Hey, welcome. This is in section 4.7, and the topic today is L'Hopital's rule. We're going to do some online lessons, at least for the time being. I'm not sure how long that we'll have to do this, but we'll do the best we can. I'll be learning with you, and hopefully you'll be learning along with me the calculus. I'll be learning how to get the technology to work and hopefully maximize our opportunity as best we can. I don't know how long this is going to be. I also don't know how I will do any assessments. So at this point, I'm worried about getting information to you so you can learn the material. We still have an AP test as far as I know, and we want to make sure you're prepared for college. So either way, we need to learn this stuff. This is not going to be stuff that's going away. So in section 4.7, L'Hopital's rule, looks like hospital, looks like la hospital. It's L'Hopital, L-H-O. If you want to do the little accent hat there on the O, that's fine. L'Hopital, no hospital there. L'Hopital's rule. This is in section 4.7 in your book. And some homework to do would be 13 through 43 odds, or every other odd, or enough to see that you've practiced. I'll also get a worksheet up for you, and then mixed review. L'Hopital's rule is a tool that helps us evaluate limits. So it's another idea for limits. But before I talk about that, I want to review a little bit about some parent functions that we've already thought about. Parent functions. First one, good old friend, y equals x squared. Again, just a real quick sketch. Y equals x squared. Good. Y equals e to the x, the exponential function. Remember, e to the x has a horizontal asymptote at practically nothing, and then it really exponentially grows. E to the negative x would be a decay, so you know that one. And y equals natural log of x. That has a vertical asymptote, and it also grows, but at a different rate. You can see all of these have different end behaviors. My question then, as x approaches infinity, the limit of all of these functions of x all approach infinity as well, don't they? Because if you look at the right end behavior, you can see, yep, that's going to infinity, that's going up, it's going to infinity, yep, that's going up, it's going to infinity. But my question is, how fast? Believe it or not, infinity can take on different sizes. For example, this infinity is going to be different than this infinity just because the steepness of that curve as it increases exponentially. Versus this one, yeah, it's increasing, but you can see it starts to increase at not a increasing rate, a very steep rate there. So think about that. How fast is really our question. Well, that's what we're going to think about. How fast? When you hear of how fast, what should you be thinking about? The rate, right? Rate of change. And when you think of rate of change, how do you think of that for calculus? What's our rate? Oh yeah, the slope of the tangent line, the derivative, okay? So we're going to use the derivative now as an opportunity to evaluate that. So here's L'Hopital's rule. If the limit of some ratio of functions as x approaches a of f of x over g of x. Now a could be a number like 3 or 0 or 1 or infinity, okay? But the infinity idea is an easy one to think about. Well, if that equals 0 or over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x, our same limit there, ratio, is equal to the limit as x approaches a of f prime of x over g prime of x. Okay? What that says is that the rate of change of these functions, so I'm looking at the rate of change of that, which one's going to get to infinity faster? We're comparing those rates of changes. And we can find the overall limit of this ratio here, f over g, as the ratio of its derivatives. Okay, so you're comparing now Not necessarily the functions, but their rates of change. We'll do a couple examples, and this should be real straightforward. So we've got x squared e to the x and log of x. You've got those in your notes. So let's try a comparison. The limit as x approaches infinity of x squared over natural log of x. Now, if this were on the AP test, and this sometimes is a free response question where you would need to show, I'll show you exactly what they're expecting you to see. Well, I'm going to take the limit as x approaches infinity of x squared. Well, what's the limit of x squared as x approaches infinity? Isn't that infinity? I mean, we can see that from the graph, if nothing else. X squared, there it is, right? And then I've got log of x, same idea. So I'm going to write that out separately. The limit as x approaches infinity of the log of x. Well, it's also equal to infinity. There it is. It's growing. It's increasing. Infinity there. Okay? So I've listed those separately. Then I need to state that the limit as x approaches infinity of x squared over log of x equals infinity over infinity. You're showing that this is, anybody remember this? This we talked about before when we were doing limits. If you got infinity over infinity or 0 over 0, it said, yeah, keep going, do some more math. Well, we can't cancel out anything, so there's no math here. We're going to do some calculus math, but we're doing something else. This is called the indeterminate. Remember that? You can't tell. Indeterminate. Indeterminate state. Okay, this limit is indeterminate. So we need to continue on. Well, if that's true, then I can write the limit as x approaches infinity of x squared over log of x equal to, and this is what I want you to write, so we know that what you're doing, L'Hopital's rule, right? Because what we did is we showed that L'Hopital's rule applies. I'm going to apply L'Hopital's rule. Well, I need to write the word limit again as x approaches infinity of, what's the derivative of x squared? We can all do that one. Back to derivatives now. We've been doing integrals for a while. Back to derivatives. That's 2x, that's right. Divided by what is the derivative of the natural log of x. Well, natural log of x is u prime over u, since x is just our u there. U prime over u is 1 over x. If you flip and multiply and simplify that, that equals the limit as x approaches infinity of what? 2x squared, which equals what? Infinity. Okay, so you've evaluated that. And what that means, if you look at the functions here, since x squared is growing at a faster rate than the log of x, we get our overall limit to be infinity. Think about that. X squared is growing steeper at x is infinity, if you think of the right-hand side of the end behavior here, compared to this side, the right-hand side of log is growing to infinity, but at a much slower rate. So you're comparing those rates. X squared is growing faster. Okay? This is the formal way that you would need to show that L'Hopital's rule applies. Okay? Write the limit first of the numerator, write the limit second of the denominator, and then show that the limit of those two ratios of functions is infinity over infinity, or it could be 0 over 0, and we'll see some examples too, because remember, that applies as well. If this is all true, if this is indeterminate, we need to see this infinity over infinity. Then you could write out that limit again as of the original function using L'Hopital's rule. Take the derivative, so that's using L'Hopital's rule there, and evaluate. Sometimes you have to reorganize, etc., and you'll get your limit there. All right? Now, if this were a multiple choice question on the AP test, which oftentimes, you don't need to go through this formal show of showing the limit of the top, the limit of the bottom, the infinity over infinity, indeterminate. So I'll kind of show you some shorthand ways. But if this were a formal free response question on the AP test, May 5th, I'm still planning on it. I hope you are too. Again, so much to be determined. So hang in there. We'll find out what that is in a bit. Let's try another one. Another example here. What about the limit as x approaches infinity? This time we'll compare x squared over e to the x. Well, like I said, this time I'll show you a little less formal. You can kind of do that in your head, right? The limit of x squared as x goes to infinity. I'm going to write that as infinity over e to the x. Well, yeah, as e to some giant power, right? Infinity squared is infinity. E to the infinity power is infinity. So infinity over infinity. We're still going to use L'Hopital's rule, an equal sign, L'Hopital's rule, equal sign, but it's less formal as opposed to the last example where I made you show, again, remember, the limit of the numerator's function, the limit of the denominator's function, and that ratio of those two, infinity over infinity. We're skipping that step. L'Hopital's rule. Okay, there it is, L'Hopital's rule. Well, L'Hopital's rule is still going to use all the steps. What's the derivative of x squared? Well, that's 2x. What about e to the x? That's our favorite function, right? E to the x. And then I'm going to try to evaluate that limit. Well, 2 times a big number is still a big number. Divided by e to the x, well, that's a big number too. Are you saying that this is an indeterminate state also? Yes. So we could apply L'Hopital's rule again. In fact, that's what you'll have to do here. L'Hopital's rule. Again, we're not saying that these functions are equal, but we're saying that the ratio of those functions, but the limit as x approaches infinity, is going to be equal. So let's apply L'Hopital's rule again. We've got the limit as x approaches infinity. Well, the derivative of 2x is just 2. The derivative of e to the x, there it is. E to the x is e to the x. So now I have 2 divided by a very big number, okay? And if you have to, you could write that out as 2 divided by infinity. You got 2 cookies divided by a giant number, an infinite number of people, you got no cookie, okay? That equals 0. 2 divided by a very, very large number equals 0, and you got that, okay? This is what I would expect to see on your tests and quizzes, which reminds me, I have no idea how we're going to do tests and quizzes right now, so don't worry so much about that. I just want to make sure that I'm not holding you up on studying. Also, word to the wise, our time, depending on how long we're out of school and doing some online work instead, our time in class is going to be limited. Depending on how quickly we are able to resume normal school schedules. So if you want to invest in a AP prep book to start preparing for the AP test, that might be a good idea. I don't know yet, certainly no one does, how quickly we're going to be back. So keep that in mind. Barron's, Princeton Review, there's all kinds of AP review books available. So you might want to invest in one of those. We really are almost done with new topics. One more unit after this, and we would be starting to be ready for review. So keep that in mind. As I come up with more ideas on how to help you review remotely, I'll share those with you too. All right? So, L'Hopital's rule. How you doing? Any questions? I mean, this is where I would stop and say, how are we doing? But if you do have questions, use the messaging in Canvas to send me a message, and we'll go from there. Let's try another one. Oops. The limit as x approaches 0 this time of e to the 3x minus 1 over x. Now, if I take this limit, again, if I wanted to show the full AP style for a free response, how to justify your answer, I suspect this could be, because I see a ratio here, so this is a possible chance to do L'Hopital's rule. Let's say the limit as x approaches 0 of e to the 3x minus 1. What's e to the 3x? When x is approaching 0, e to the 0 is 1 minus 1 equals 0. What about the limit of our denominator's function? Limit as x approaches 0 of x. Well, that clearly is equal to 0. So the limit as x approaches 0 of e to the 3x minus 1 over x equals 0 over 0. That again is indeterminate. Okay, indeterminate. So 0 over 0 or infinity over infinity says yes, L'Hopital's rule applies. So I'm going to go back up to my original function, and I'm going to write L'Hopital's rule, because I'm telling my grader, either me or your grader that will be grading your work from the on the AP test, is that we've applied L'Hopital's rule. We've shown that the conditions are met, and now it's time to do L'Hopital's rule. Well, we still need to write the word limit because I haven't evaluated the limit as x approaches 0. But what's the limit of e to the 3x? Remember, it's e to the u times u prime. So e to the u, still e to the 3x, times, because of the chain rule, the derivative of 3x with respect to x is just 3. So 3 e to the 3x minus, well, the derivative of a constant 0, so we're good there, divided by, what's the derivative of x? Well, that's just 1. Now, be careful. A lot of times when people see zeros, it's like, oh yeah, the limit's 0. No, not so fast. That's equal to 3. Notice how I'm not writing the word limit anymore because I'm evaluating it. Times e to the 0. E to the 0, 3 times 0 is 0, so e to the 0, that's 1. So 3 times 1 equals 3. We've got our L'Hopital's rule, and we find that our limit there is equal to 3. All right? Questions? Yes. Another example then. The limit as x approaches negative infinity, because you could have negative infinity, of x squared over e to the negative x. E to the negative x. Well, with this one, let's see. I'm not going to do the formal show. I'm just going to do the quick check here. Negative infinity squared, because you can have negative over negative. Is that our case, though? Well, no. Negative infinity squared is infinity squared, so that's, sorry, negative number squared is a positive, so that's positive infinity. What about e to the negative x? What's that graph look like? E to the negative x, that's the decay function, right? So that's going to start out high and then taper down to 0. But as x approaches negative infinity, that's to the left. So that's still positive infinity. So, sure enough, infinity over infinity, L'Hopital's rule applies. Well, I'm going to write L'Hopital's rule, and this I would need to see for your evaluations here, assuming there will be some. We'll worry about that later. Derivative of x squared, 2x. Derivative of e to the negative x, well, that's going to be e to the negative x, then we've got a negative sign. Okay? So 2 times negative infinity is going to be negative infinity. Okay, still large. Divided by e to the negative x. So I've got this here, e to the negative x, as x approaches negative. But that's going to be positive infinity if it were without that negative sign. But then with that negative sign here, this one right there, makes it negative infinity. So negative infinity over infinity, yep, that's the same. So it's indeterminate. I'm going to apply L'Hopital's rule one more time. L'Hopital's rule. And that tells us to take the derivative one more time. Limit x approaches negative infinity of 2. And then e to the negative x again is e to the negative x times negative 1. But we've got that extra negative 1, so it's just going to be positive e to the negative x. Well, I can evaluate that now. It's 2 divided by infinity, which is 0. Okay? Let's try a couple more. This looks a lot like ones that we might have seen before. The limit as x approaches 0 of sine x over x. In fact, you were told that this was way back when, one of those special rules that I told you just to memorize. You know what? Now we've got enough calculus to say, yeah, you don't need to memorize this. You know this. You know this, how to do this problem, no problem. I'm going to just do it real quick and not do the full AP style, but what I would want to see on a test or a worksheet. Evaluate that limit as x approaches 0 of sine of 0. Well, if you need to review your unit circle, which I hope you are, that's 0. And x approaches 0 as x, yeah, there it is, 0. 0 over 0. Well, L'Hopital's rule works. So if you forgot this one that I told you to memorize way back at the beginning of the year, I'm going to now take the derivative of those. What's the derivative of sine? And you would still need to know that, of course. It's cosine x, all right? Divided by, what's the derivative of x? 1. Can you evaluate that? Of course you can, because it's not 0 over 0. This is not indeterminate at all. It'd be the cosine of 0 over 1. That's 1 over 1 equals 1. So that was one of those limits where I told you just to remember that. A lot of times we think, oh yeah, it's 0. No, it's not. It's one that you can do. Okay, so that's one I told you to memorize. Let's try another one here. What about the limit as x approaches 1 of x to the third plus x squared minus 2x over x minus 1? Well, x to the third plus x squared minus 2x, that looks like that would factor. I wonder if x minus 1 is a factor. Before we had L'Hopital's rule, we'd have to try to factor that and get it to factor out and factor out an x and look for pattern errors, like especially if L'Hopital's rule applies. So let's check if L'Hopital's rule, because I'm already suspecting a 0 on the bottom, but let's, in fact, we can write that in, right? We can evaluate that one. Plug in a 1 here, we get 1 to the third plus 1 more, 1 squared, so 1 plus 1 minus 2. Yep, sure enough, it is 0 over 0. So this is our indeterminate. L'Hopital's rule does work. Now, does this mean that this is going to throw away all our limit ideas from before? No, hopefully not, because limits will be a big part of your AP test. And if you, and your next year, I mean, I'm getting you ready for next year. Yes, the AP test is still looming ahead, but at this point, I want you all ready for your next year of college math. So L'Hopital's rule says, well, take that derivative. You can take that derivative, can't you? 3x squared, sure. Whoops, I haven't taken the limit yet, so I need to write that. Limit as x approaches 1. 3x squared plus 2x minus 2. Is that right? Over derivative of the bottom one, that's just 1. That's easy. Again, no worries here. So it'd be 3 plus 2 minus 2. Doesn't that give you plus 2 minus 2? We're evaluating that limit, so I don't have to write the word limit anymore. That equals 3. So there's your limit there of that one. Before we'd have to divide out and cancel our common factor between the top and the bottom, but we've got that one good to go. Okay? So, some summary ideas. Remember, and this is an important one, if you're going to do the formal show, if this were an AP kind of question where you had to separate the numerator and the denominator, show finally that the ratio of those two functions as the limit approaches whatever your number is, infinity over infinity, or 0 over 0. This is showing it the formal way for an AP test, versus this is the work I would expect to see you do on our tests in class, but also, scroll it down here, but also for the multiple choice. It's a real shame, and I will have work problems for you to practice on tomorrow or next time. I'm not sure when tomorrow will be, but the next time I'll put up a worksheet that will be kind of a review problem set to have you practice some more. For now, I'm hoping that you crack open your book, but where it's 0 over 0 or infinity over infinity, here's 0 over 0 here, where L'Hopital's rule doesn't work and you can get a wrong answer if you just start using L'Hopital's rule. So don't throw away that. Okay, so step 1, or reminder, check for 0 over 0 or infinity over infinity. Okay, check for those, which is the indeterminate form. Before you use L'Hopital's rule. It's just like some of the other, like intermediate value theorem, you had to check for continuity. And so those kind of conditions need to be met before you can start applying theorems that don't apply if you don't have the conditions. Okay, you need to check those. Number 2, you may need to use repeated use of L'Hopital's rule. And we saw those in a few of the examples. So that is all possible. So keep that in mind. You might see those. Okay, you might be needing those. Reminder number 3. Just got an email there. Reminder number 3, don't forget. All of the limit evaluation techniques that we learned before. And to help you remind yourself of those, after we do some practice out of the book and an extra worksheet, I'm going to be giving you more mixed review, where some of them would be L'Hôpital's rule questions, some of them won't be, and they'll be all mixed in. So it'll make you remember those. So we use this as our first round of getting ready for the AP test. And finally, remember what you're doing. If you're ever asked a question, why does L'Hôpital's rule work? Well, you're comparing to find a ratio of two functions, their limit. You're comparing the rates of change. I'm hoping by now that rates of change makes you remind yourself of taking derivatives. That's the slope of the tangent line, etc. If you have the indeterminate form. Indeterminate form. 0 over 0 or infinity over infinity. Now, as a hint on what's coming, you might have functions that you might have to work to get the intermediate form. So there might be products, and we'll find some examples to kind of display that the next time we visit. Okay? So again, stay well. I hope everybody's taking it easy and working to stay healthy. But also, as we get closer and closer to figuring out what we're doing here, I'll be posting more of these videos, and hopefully we'll be back in school as soon as possible. All right? If you have any questions in the meantime, send me a message on Canvas, and I will talk to you soon. Thanks.